This meeting is being recorded.
Thank you. Cool. Welcome back to our CS 181 languages course. So I've been super excited about what we're going to talk about today for a long time. I've been I couldn't sleep all last week, being so excited about what we're talking about today. Before we do that, though, we're talking about this RASP language. I mentioned that last time. Before we get into the technical stuff, though, quick announcements that your RAG evaluation homework all graded. Most people got full credit. A few people got -1 point if there was just something that annoyed me about it. So 1 point out of 1,000,000 points is not going to make a big deal at all in your grade, but I just figured I would register my annoyance. If, for example, the Python file is not in the RAG news folder, or there are weird binary artifacts in the GitHub repos, or there's probably some other things too that I didn't write them all down. But if for whatever reason you got 999,999 points instead of 1,000,000 points, then there's a note saying what the problem was. And then a handful of people I couldn't figure out where you put the accuracy scores in your GitHub repo, and so I just temporarily gave you 0 points. If you just email me telling me where to find that, then I will regrade it, and you'll get a lot more points. There's no major big things, consistent things, mistakes that people made, so nothing that I really want to go over in class. But a handful of people asked me about different coding conventions, what would be good or not good. And so if you do have questions about that, about your code, I would be happy to sit down with you one-on-one for 10 or 15 minutes and walk through things that could be better. I guess especially the people who missed the 1 point here, that might be a useful thing to do. Let's see. Any questions about that or anything administrative in the class? Okay. Everybody else is equally as excited as I am to talk about this RASP thing and doesn't want to delay it even more. Yes, excellent. Okay, so I have a little high-level thing that we'll do here for 10, 15-ish minutes, and then we'll get into actual coding technical stuff. So we will use RASP to understand what transformers are capable of. And what I mean by that is we'll be placing, eventually, the reason we're doing this is we're going to be talking about lower and upper bounds on what a transformer can compute. So again, the transformer is this generic name for these architectures that things like ChatGPT, Llama are built off of. All of those are transformers. Examples of things that we will be able to see are that transformers will never be able to play perfect in-by-in chess. We'll talk about what that exactly means for it to be perfect and for it to be in-by-in chess, but it's just computationally impossible for that to happen. And then we'll also see that certain transformers can sort their data and others cannot, and that will give us a good hint about which types of transformers are good to use and not good to use, because sorting is a very fundamental problem that a lot of things reduce to. And I have probably 10-ish examples of things like this that we'll be able to see that transformers prove that they can or can't do, that we'll get to after we talk about the mechanics of programming in this RASP language. Another thing, so we're going to be focusing on these perfectly trained transformers, ignoring the ways that training can reduce performance. So last week we talked about this paper that showed how this just training methodology, if you're using teacher forcing, can reduce your performance no matter what else is going on. This week, we're sort of ignoring all of that training stuff and just focusing on whatever a perfect transformer would be, the best possible of these models. RASP itself is what we call an esoteric programming language, or an SOLang. These things are very popular. There is this whole community of SOLang people. This list of SOLangs right here has something on the order of 10,000-ish SOLangs inside of them. RASP isn't even in the list over here. But so this is just I don't know, a fun thing that people do, make these programming languages that do weird things. They're programs that they don't like. You don't use them to write real programs. Instead, you use them to explore some aspect of programming. And in this case, again, we're exploring the transformer architecture and what it's fundamentally capable of. There's this quote by this guy, Alan Perlis. He's a very famous person, one of the first computer scientists, first person to basically invent programming languages, different programming languages. He was awarded the first Turing Award for inventing programming languages. The Turing Award is like the Nobel Prize for computer science. And he also has this famous list of epigrams on programming, just a bunch of sort of funny one-liners that have a truth value to them. And one of those more famous ones is that a language that doesn't affect the way you think about programming is not worth knowing. So this language right here is definitely going to change the way you think about programming, and so it's worth knowing from that perspective, but it's not something like Python that you would actually do to implement something real. So there's some sense where it's not worth knowing because you can't do a real program with it, but it's definitely going to change the way you think about programming. Maybe as an aside, like sometimes I like to think about how many people have studied the things that I'm studying. So like with this RASP program right here, my estimate is less than 1,000 people have like done anything remotely serious with this RASP program. So you all will be joining this elite group of less than 1,000 people. I'm also fairly confident that it's never been taught at all in a course before, whether that be like a undergraduate course like this or a graduate level course. The only people who have used this at all are researchers who have sort of stumbled on it by themselves and done something interesting. So real quick, high-level example to get us started. On the left-hand side here is a bunch of code. By the end of this week, hopefully we'll be able to understand what this code is doing. And then on the right-hand side over here is pictures of transformers. You have likely maybe seen some sort of pictures that look like this bottom output down here. This top output is the output of the RASP program. And they're just showing that the RASP program output is very similar to like actual transformer output, like actual things inside of ChatGPT. So this is our motivation, where we're going to be able to understand something that looks like this. Almost one last thing for us to talk about here. So RASP, we're going to be using it in a form that's actually like a pure language form. It does have several different Python libraries. I'm not going to go into these in detail, but the point of these is just that other researchers are building on this RASP program, doing interesting things with it. If you've heard of this phrase, mechanistic interpretability research, this is one of the ways that people are trying to understand like how transformers, how ChatGPT is working under the hood, and RASP is one of these tools for mechanistic interpretability research. Okay. Last thing right here, bullet point. Currently, no tutorials exist for the raw RASP language, the thing that we're doing. I have sort of a tutorial typed out for us here that we're going over now. Again, this is the only tutorial that exists anywhere in the world. You won't be able to ask ChatGPT for help with this because it's not in the training data at all. And you won't be able to Google other things because they don't exist. Everybody who has used RASP in the past has just read this paper and understood everything directly from the paper without any examples. I often like to look at the authors of things that we're looking at. We've done that before. So this person here, Gail Weiss, she is the author of RASP. So we're looking at her work. She was a PhD student in Israel when she was doing this. This was 2019, I think, when she first wrote it. So 5-ish years ago now. And now she's a postdoc somewhere in France. Let's see. Okay, so for the homework, I haven't created the homework for you all yet. We'll have that for you probably on Wednesday, maybe next week, depending on how much time we spend on this. But the basic idea is you're going to need to know how to write this RASP code in order to solve different problems. And some of those problems will look like they'll actually be solvable in RASP, and you'll need to provide the implementation for me. Some of those problems will not be solvable in RASP, and you will need to explain why they are not solvable. And so this is different than the sort of programming stuff that you've ever done in Python. You've never before been given a task that is not solvable. But in this case, you will have some tasks that are not solvable in this language, and you'll have to be able to identify why that's the case. And we'll even have some tasks that nobody in the world currently knows whether they're solvable or not. And so you all could potentially make some contributions to our scientific understanding of the world of transformers by figuring out if there's a solution or not. Okay. Any questions at a high level before we get technical fun details? Yeah, thanks.
What is the homework deadline?
Question is, when is the homework deadline? Good question. Definitely not this coming week. It'll depend on how much time that we spend doing the RASP stuff here. We might finish on Wednesday, or we might go into next week Wednesday, depending on how much, if you all share my enthusiasm for this, and we go into a lot of detail. But you'll have 2 weeks to do it. So not this coming Sunday, maybe the one after that, maybe the one after that. Yeah. Oh, question is, why is there no tutorials published? The answer is because this is the sort of thing that the people working on it don't need tutorials for. Yeah, so yeah, I think this is the right way to explain how transformers work, thinking about the breaking things up into pieces about like training versus the in principle what's possible. So I think the future explanations of ChatGPT will do something like this. But at this point, this is like super theoretical mathy people who just need like a 1-paragraph explanation of what this language does, and then they can use it. And it's not geared towards like the general public. There's a lot, so again, like a lot of these sort of SO languages that exist, and I'm just randomly scrolling through thousands of them here. None of these have tutorials published for them. The expectation is that if you're going to do any of these, whatever like the cool thing about it is, then you have enough programming background at this point to sort of figure things out yourself. So one of the reasons why I want us to do this is because, well, first of all, like I've mentioned so far, getting the actual knowledge about transformers and large language models, I think that's good. But I also think it's the case that one of the weaknesses of our CS program here is that you don't get exposure to enough weird programming languages. And so I want to expose you to a very weird programming language that will, as Alan Perlis wanted, expand the way you think about programming. Yeah, so good question. Hopefully that sort of answers it in a satisfying way.
Is this a good final project territory?
There's lots of good final project territory stuff here that, so in the solving or not solving some of these problems, that would be fantastic final project. Yeah, there's actually a handful of extensions to RASP that I've come up with just in the past week because it's been so exciting to me that we might talk about that could be good final project territory stuff. But yeah, so lots of potentially interesting stuff here for that. Okay, maybe one last thing. I've said that like 5 times now. One last thing before we actually get started technical stuff. There was a good question over here from Rowan about how the RASP repository was structured and what makes good technical structures here. That there's this tests folder, and inside of that is a whole bunch of Python and other shell scripty things running tests on RASP. And is this a good structure, or is it more standard for these tests to be just incorporated directly into the GitHub Actions? My answer is that the way I see GitHub Actions and the way I think the vast majority see it is that this is supposed to describe like an environment and not your test cases. This is the environment that the test cases happen in. And so there's just a handful of things up here designed to like set up the problems. And then at the very end, a one-line code that actually runs it. For us, our one-line code was the calling the doc tests, or but that's a very standard sort of practice, is that the workflow up here, the GitHub Actions, just defines the environment, and then you have your actual tests somewhere else. And that lets you, for example, run those tests on your own computer before pushing to GitHub or doing other things like that. Since we're on here on the GitHub repo too, some things to talk about is there's this install script setup.sh. I personally find the way that this is structured to be disgusting. This setup.sh script in general, so shell scripts, if you run them, they can do anything arbitrary to your computer. They're not guaranteed to do the things that you want, like install things. And the sudo command over here is requesting root or admin privileges on your computer. That's not something that I give out lightly to other people. So when I installed this, I did not run their shell script here. Instead, I read through it, saw, oh, there was only two, they have this like 100-line thing just to install 2 packages. I already have those 2 packages installed. I don't need to run this shell script here. This other community is not in the Python world. This would be a standard thing to do. Python world, not a standard thing to do. This author here, Gail, she, well, coming from Israel, Israel's very much a C-oriented, low-level programming place. I mean, they do Python, but they would, like, all their intro programming classes would be in C, something much more low level. And in the C world, C programming world, this is a very standard thing to do. Okay, actual technical stuff now. So starting this program with this rasp.sh file right here. I already have a terminal opened up. Let's reset that into this RASP folder right here. And I'm going to walk through things side by side with the code, my README file on the left-hand side, and then on the right-hand side, this terminal. Let's see if I make this a little bit bigger. And the way we start this code, I'm in my RASP folder right here, is doing the / what they call it, rasp.sh, like this. And make that just a little bit bigger so it's easy enough to see. And then on the left-hand side, again, this is just our GitHub repository. And I'll have a handful of code examples over here. We'll walk through what the code examples do I'll type them in here on the right-hand side and explain what's going on. Before I get started, any questions about what my setup is, how to follow along? My recommendation, again, is to actually like follow along with the RASP code over here, trying to reproduce the things that I am doing on the screen, and because you'll have to do that for your homework to be able to implement some of this code. Okay, so the fundamental building block of RASP is what's called a sequence operation, or SOP for short, and that converts an input sequence of length in into an output sequence also of length in. And in RASP, the length cannot be changed. So like Python, you can change the length of your lists. There are different types of lists, like tuples versus lists versus sets. That's not the case in RASP. There's only one type of thing, which is a sequence, and it always has exactly length in. There are 2 what are called primitive SOPs in RASP here. Something that is primitive to a programming language is something that is built into the programming language, and it is not something that is built from other parts. So these 2 primitive SOPs are called tokens and indices. And these ops represent the input information into a transformer. I'm not going to go too much into detail today about how the things we're talking about relate to transformers. Instead, we'll just talk about the programming language itself, try to get a handle on the programming language, and then in the future, maybe Wednesday, maybe next week, we'll talk about how these things actually physically relate to the transformer architecture. But these SOPs, they work one of the things that you can do with them is just like function application in Python, where you have the name of your SOP on the left-hand side and then the thing that you're applying it to on the right-hand side. So this tokens, when you use it like this, is like an identity function, tokens, and then hello world, like that. And we get hello world as the output down here. This equals, and then the square bracket right here, this means that this is all a sequence. In Python, the square brackets and the quotation marks are different things, that this is a string and this is a list in Python. In RASP, these are the same things. This is just syntactic sugar for this thing down here, because this is a lot easier for us to type than this thing down here. But the output, they're going to output it in a more raw form that looks like this. So we can see here, hello world, one letter for each of the letters in our string up here. The other built-in primitive SOP is indices, and hello world, something like that. Without a typo, indices like that. Looks like that. And indices is just like a counter starting with 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One number increment for every input token that we have. The couple of gotchas here. So in the tutorial thing on the left-hand side here, I've tried to label gotchas, things that are going to be awkward for you all not having been exposed to a lot of programming languages yet, but that are maybe for the authors and researchers who use this sort of thing, like obvious sort of things. So not mentioned anywhere in the documentation. But the first of these awkward things is the semicolon. All the commands in RASP end in a semicolon. So I press the up arrow here on the right-hand side to get back to my previous command. If I don't include the semicolon, then you get some sort of weird-looking output like this. It just means that the command is being continued onto the next line. And if you add the semicolon, you'll get that output down. So commands in RASP are semicolon terminated. There's a common pattern in programming languages other than Python that they have semicolon termination. Okay, strings get tokenized at the character level. So here, when I did hello world, each of these things inside of the comma here is one individual token, and by default, this happens at the character level. If you want things to happen not at the character level, then you have to use this square bracket notation explicitly. I'm going to copy and paste this tokens right here. And you can see now that there are, so hello and world, those are my two tokens down here in these square brackets. And if I copy and paste the indices right here, then we can see that the length of this sequence only has length 2 instead of the length 11 that we had before. It turns out that this is not an interesting thing to do in RASP, that RASP is going to focus on stuff that happens after the tokenization, but it's easy to come into weird like error messages if you're not familiar with this. Next part down here, so RASP supports sequences of 4 different types: strings, bools, ints, and doubles or floating point numbers. And so here's just some more examples here that you can use true and false values, Boolean values, the same way you do in Python, trues and falses. Here's the final sequence there. And you can use numbers as well. Tokens 1, 2, 3 gives you these 1, 2, 3 right here. Yeah, Nolan.
Are these types strings? Strings or is it?
Yeah, that's a good question. So the output down here in the parentheses over here, it says strings as the type of this number right here, even though I input numbers, these are integers right here. This is a, let's see, it's the right way to phrase this, a sharp edge about the RASP system that RASP is designed not for user friendliness. It's not designed to make like you all more productive as programmers. It's designed to help you all understand better what's going on inside of the transformer. And there's a lot of, again, these sharp edges that the authors did not put in the time to polish up because it's just not a useful thing to do. So in this case, this sharp edge here is that these, in the display portion of this 1, 2, 3 here, these integers are getting converted to strings to display, but they are actually not strings under the hood. They are integers under the hood. Yeah, good question. Any other questions so far? All more or less straightforward so far. Let's see, if you have one of these SOPs and you apply something that is not a sequence to it, you'll get an error. The error messages in RASP are very weird. Again, like I've built many programming languages, so I understand why the error messages are the way they are. You all have probably not, and so you probably will not understand why the error messages are the way they are. And again, this is an artifact, one of these sharp edges that these authors have more important things to do than make these error messages look nice. And so you probably will not find the error messages helpful. Or the way that you'll find them helpful is that if you see something that, like in the gotcha up here, I label this is going to get an error message, then actually type it in, see what the error message looks like, so that if you see something in the future that is an error message that looks sort of like this, you can figure out what's going on. In this case, it says the sequences, selectors, expect non-empty iterables, got one. It means that this thing that's passed into tokens needs to be a sequence somehow. Yeah, there's also a lot of inconsistent terminology about like, sometimes they call things sequences, sometimes they call things iterables. Those are synonyms for each other. This selector is something different that we'll see later on. So figuring out what exactly is a synonym with what is a little bit hard here. Okay, so these SOPs always take exactly one parameter, and if no parameter is provided, then a default value of hello is used. So if we can just type tokens like this, semicolon, and it by default passes in hello. You can see it right here, tokens of hello equals hello like this, or just type indices like that, and we get the 0, 1, 2, 3, 4 default value for hello. This is the most practical way of doing things, the vast majority of the way that you'll do things. And these up here, just for example's sake, everything else is going to use the defaults. You can set the defaults with this set example command. And I'm going to copy and paste this over here. And you'll notice that this does not have a semicolon at the end of it. So another one of these sharp edges is that there are some commands that are not semicolon terminated. And if I do that, then tokens again, then we can see that my new example is hello world like this. If I do the set example with hello world like that, then my new tokens is like this, where we're tokenized at the letter level instead of the word level. Their PDF paper that goes over things shows one example of using this set example command, but they've never, for example, mentioned that it is not a semicolon terminated command. If you add a semicolon at the end of set example, you get a very weird and scary error message, and it says nothing about that set example is supposed to not have a semicolon at the end of it. It's just what it's saying here is that how I read this, how I know to read this is that when you have a semicolon, it's expecting one of these things to exist before the semicolon. One of those things is not before the semicolon, and so there's an error. But yeah, less than helpful. So no semicolon there. Okay, so this is actually like the only sequence operations that are built into RASP. These are the only sequences that exist inside of ChatGPT or inside of any transformer architecture. And all of the fancy computation happens by combining this tokens and this indices together in fun ways. And so this is what this next section is, defining new SOPs element-wise. So again, the SOP is this sequence operation. Indices and tokens are examples of sequence operations. And so indices right here, 0 to 10. We're still on the hello world example right here. And I can do indices plus 1 to add 1 to all of those indices. So now we're starting at 1, going to 11. It's wrapping around right there. That's an 11. Or I can do indices times 2. And now it goes all the even numbers up to 20. These operations all happen element-wise, which means there's no way at this point to combine, say, like the information from the 2 position right here with the 4 position. Your only, whatever math operations you have here are all happening just at the individual element level. One gotcha here is that you might try to do something like this, where we saw before that you can do something like indices of hello, hello in strings right there. And that works. This looks like a sequence sort of thing, so it looks like you might want to try to add 1 to all of this, but this is going to give you another crazy error message. Just unsupported operand for plus, just val, and int. Like, what does that mean? It means that you can't do this sort of function application to SOPs and then do something with it. If you're doing this function application, it has to be the very last thing that you do. So what we were trying to do right here, find all the indices for this sequence and add 1 to it. The way to do that is indices plus 1, defining a new SOP like this, and then passing hello to that new index. So something like indices plus 1, and then passing hello like that. That works. No error message here. It looks awkward syntactically, but that is semantically the right thing to do. The same semantic meaning as this, or the same semantic meaning as this up here, just with the hello instead of the default. Any questions so far? Is mostly tracking? Yeah.
And just to make sure I got it, if you want to do a group of operations, you'd add them all together in like a first set of parentheses and then.
Yeah. So here, if we wanted to combine multiple operations together, so like indices plus 2, and then maybe times 3, something like that. So first add 2 to everything, then multiply by 3. You can group all that together, and then hello that at the end like this, and that's syntactically fine. Good. No? Okay. So we can create new SOPs. So this right here is an example of an anonymous SOP. In programming languages, whenever we create something and we happen to assign a name to it, we call that an anonymous thing. So this is an SOP. It doesn't have a name, so this is an anonymous SOP. We can name it using standard like equals assignment, like you might expect. So I plus 1, I for indices equals indices plus 1. That is a thing that we can do. And now we can use I plus 1, however we might use any other SOP. And we can, through just the tools that we have so far, build very, very complicated SOPs. It turns out that you can do arbitrary computations on an individual token with the tools that we have seen so far. Question?
Yeah, so right now, is your set example set to hello world?
So in order to see what my set example is, I can do tokens by itself. And so the set example is hello world, the entire thing, yes.
Is there, is it inside of the square brackets?
And it is not inside of the square brackets right now. It is just the string hello world. And so it has 11 individual letters inside of it. Yeah, so at this point, we're just getting into like the weird syntactic things about this language, not getting yet into the what is like the actual interesting parts about the power of this language and how it lets us represent transformers. Just a lot of weird syntactic things we need to get through before doing that. Okay, so these element-wise operations up above, we've seen all of them just happening on one variable, one SOP at a time. We can do multiple SOPs at a time, but again, these will happen element-wise with each other. So if I do indices plus indices like this, that is the same as indices times 2, spelled correctly, indices times 2. It's I always type out indexes when I'm programming like that. Other people like indices when they're programming. So I'm getting a lot of typos here with my indices. But yeah, any like arbitrary math operation that you might think about, including ones that involve your previously defined SOPs, you're allowed to do. And you can, again, make arbitrarily complicated functions this way on an individual number at a time. Notice here when I did the division, I had to do divided by I plus 1 instead of indices. If I do indices divided by indices, then we're going to get a division by 0 error because indices contains 0 inside of it already. So when we get into the actual like interesting algorithms, this will be a common idiom of adding 1 to your indices before doing the division. Okay, all of these are on numeric types up here. We can do things on Boolean types, so like indices less than 3. Here we get, we've converted indices used to be numeric, the less than operation, converting it from a number to a Boolean true or false value. And so these first 0, 1, and 2, those are all less than 3, and everything else false over here is greater than 3 or equal to 3, and so these turn out to be false. Weird error messages happen again if you combine types in a non-expected way. So I'm going to do my set example back to hello here. And so if I just look at tokens by itself, this is HELLO, these are strings. If I do hello plus 1 like this, then, sorry, not hello plus 1, tokens plus 1, then we just get this something went wrong error message. Super helpful. Yeah, be careful about your types, tracking through what types you're adding or manipulating. The two main ways of casting types are this indicator function and this round function. Indicator will convert something from a Boolean to an int, and round from a float to an int. So indicator of, well, we already saw, I'll do indices less than 3 again. Indices less than 3 gives us a bunch of trues and false values. If we apply indicator on that, then that'll convert that to ones or zeros. 1 for true, 0 for false. The round function over here exists. So round, divide everything by 2 right here, then round it. We'll get 0, then 0 because it's 0.5 rounded, then 1, then 2, 2. The round function behaves a little bit weirdly. It ends up being very important for a lot of examples, but it behaves weirdly. Let me make this a little bit bigger to illustrate that. So indices right here, 0, 1, 2, 3, 4 are the indices. Indices divided by 2, semicolon. We get 0, 0.5, 1, 1.5, 2. And then you might expect, for example, that this and this both get rounded in the same direction, but that's not going to happen. When I do round of indices divided by 2, we get 0 is 0. This 0.5 right here got rounded down, and then a 1, and then a 2. This 1.5 right here got rounded up, and then a 2 over here. Why are they getting rounded in different directions? It's because it turns out that 1.5 does not have an exact representation in binary floating point numbers. Similarly, 0.5 does not have an exact representation. And so this number here, even though it's displayed as 0.5, is actually like 0.4999923 something. And this is actually 1.500000012. And so the round here, you have to be a little bit careful when you're doing things that involve rounding. It's also the case that there is no ceiling or floor functions like you might have for other languages that you're used to. You have to implement any sort of conversion from floating points to integers using the round function. So like ceiling does not exist. The ceiling function or the floor function, those don't exist. Okay, so that's all just weird syntactic stuff so far. Yeah. No. They could be implemented in, based on the things that do exist, but they are not so far. Yeah. Yeah. Offhand, I don't know. So like indices gives me this, and let's change set example hello world again. So indices gives me that, indices divided by 2. So now we have a 2.5 in here somewhere right there. And if we do round of that, then I think, so this is the 1.5 being rounded up, then the 2 being rounded to 2. This is the 2.5 being rounded down to 2. And yeah, there's not like a good way of predicting whether the number is going to round up or round down. One thing that we'll see an example of this later, but one thing that you can do is subtracting some like small-ish number like this. That guarantees that everything is going to be just below the 0.5 level, and then the rounding, it'll always be like 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5. But we'll see this like with an actual example later on where it makes sense contextually. The important thing at this point is that there are types in this language. There are some ways of converting between those types. Indicator and round are the only actual ways of converting between types. And they will behave weirdly, and you'll probably have bugs in your code expecting them to behave one way and then not behaving that way. And again, no tutorial on that. That's just something that people were expected to figure out on their own playing around with things. Good question so far. Any other questions? Okay. So control flow. Anytime you have a programming language, you need to somehow understand how to make the programming language do something different based on different situations. And that is what we mean here by control flow. So RASP is not a procedural programming language. So Python is an example of a procedural language where the execution happens one step at a time. You go from one line of code down to the next one, and you use different things like if statements and functions and for loops to decide how many times a statement will be executed or whether a statement will be executed. RASP does include all of these things. It does include if statements, functions, and for loops, but they do not behave the way they do in Python. So what we're talking about now is not just weird syntactic stuff, but weird semantic stuff, like things that that are actually different. When we're in general with programming languages, we try to make a distinction between the semantic weirdness and the syntactic weirdness. Everything up above is just syntax, like what causes an error message. The stuff that we'll talk about now is semantics, like why is the code not doing what you think it should do. So again, not a procedural programming language. And these if functions and for loops, they don't actually affect the control flow like you're used to. So let's see this with if statements first of all. They are what are called ternary operations, which means that they take 3 parameters. So here's an example, -1 if indices greater than 1, else 1. Anytime you use an if statement, you must also have an else clause. And in RASP, both branches of this if statement will be executed. In Python, only one of these branches will be executed. In RASP, both of these branches will be executed. So let's walk through what exactly is going on right here. So what I'm going to start with, so we have -1 like this, -1 by itself, that is a valid command. It just has the output value of -1 right here. Let's remind ourselves what indices look like here. It's, and I'll set my example back to hello world, back to just hello, so it's smaller. Set example hello. Indices are the numbers 1, 2, 3, and 4. And this if statement is going to happen element-wise on everything, on all of the elements in our indices right here. So if I have indices greater than 1, indices greater than 1, I have false, false, true, true, true. All of the false values will take the value of this else branch over here, else 1. All the false positions will get 1. All of the true positions will get -1 over here. So we say -1 if indices greater than 1, else 1. And so we get 1 in all of these false positions. Everywhere there was a false in the condition here being indices greater than 1. Again, this is an S op right here. Indices is an S op. So indices greater than 1 is happening element-wise. It gave me this sequence right here with false, false, true, 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 5 entries inside of it that are Boolean entries, either false or true. And for each one of those entries individually, we apply this if statement. And if it was true, this thing right here evaluated to true, assign -1. Only the last values over here are equal to true, so they get -1. And the rightmost value over here is the else statement. So if it was false up here, these false values get the value of 1. Get the values of 1 right here. This is an important syntax to make sure that you understand because, again, if statement's super important in programming, and the if statement here behaves weird. In order to implement lots of interesting things, you'll have to understand how these ternary if statements work. Any questions about those ternary if statements? Is this something that people were mostly tracking with? See a couple head nods.
Is true is greater than 1 evaluate to true?
Question is true greater than 1 evaluate to true? It does not. So this is something that in Python is a well-defined thing. In RASP here, I have no idea how they automatically convert things from Boolean to non-Boolean values. So I would be very careful, never write a program that's somehow comparing Boolean values to numbers. I wouldn't know what to expect from that. Okay. Yeah, so if statements, very different than the if statements in Python. These are ternary if statements. Ternary if statements by themselves are actually fairly common in programming languages. Python even supports a version of ternary if statements. But this element-wise operation, not common, and Python supports nothing like this element-wise operation of ternary if statements. Okay, so functions are defined with the def keyword similarly to Python. So this is an example of a function right here, define the max between A and B, and return A if A greater than B, else B. Let's go ahead and I'm going to copy that into the terminal over here so we have access to this function. Okay, and in this case, it's saying that I can't do that because it's built into the standard library. So max is something built into the standard library, and it's defined in this way. What it's doing is, again, it has this just if statement right here, the ternary if statement, that for every these A and B, there'll have to be SOPs being passed in. If A is greater than B at a particular given position, we'll return the A value. If A is not greater than B, then we'll return the B value. So if we do max of, say, indices and let's try. So indices minus 1 to the third power, semicolon, to the second power, semicolon. So this is going to be, we're going to compare this SOP right here, 10149, with the original indices. And the original indices looks like this. In the very first position over here is a 0, so this 1 is at the same position as this 0. This 0 is at the same position as this 1, and then 149, 2, 3, 4. So this 1 and 2 bigger than the 1 and 0, 0 and 1 up here. Everything else in the first SOP, this SOP right here is larger. So if I do max of indices, comma, indices minus 1 squared, like that, then it'll take the max of those 1, 1, 2, 4, 9. These functions, they can have SOPs or a couple of other things as parameters for them, but it's very important to observe that these are not actually SOPs themselves. Max, it sort of looks like an SOP because it has like this function syntax, application syntax, similar to how we saw the function application syntax on tokens and indices. But these are not SOPs. These are functions, and they're very different things. It'll be important, again, later on to keep track of what things are SOPs and what things are functions. Maybe here, the example that I have right here is actually probably simpler than the one that I did in the terminal on the right-hand side, that take the max of indices in 2, then it'll element-wise compare 2 to all the indices and keep whichever one is bigger. So the first one's bigger, this was 0, and then 1, and then everything else coming from indices. Any questions so far? Yeah, it's a good question. It turns out that there is this might be a totally unhelpful answer, but I'll start with the unhelpful one before I say the helpful one. It turns out there's a bijection between functions and SOPs, so fundamentally there is no difference between them. And if this was like a real programming language and not an SOLang, then I would expect there to be like actually implementation-wise no difference between them. But because this is an SOLang defined for just like one particular purpose that somebody did in their spare time over a couple of months, and it's not like Python, which has a multi-million-dollar foundation with professional developers working on it day in and day night to make it ergonomic to use. There's just a weird syntactic difference between SOPs and functions over here. And we will need to, in the future, remember was something defined by using the DEF keyword to make it a function, or was something defined by just using like A equals indices. If you're defined with an equals sign like this, then you're an SOP. If you're defined with the DEF keyword, then you're a function. And power-wise, they can both do the same thing. Again, there's a bijection between them, but we'll need to keep track of how it was defined. Is that?
So they're syntactically different, but they're syntactically different, but semantically the same.
Yes, and maybe functions in one variable are semantically the same as SOPs. If we have something like this, max with 2 variables over here, that cannot be done with an SOP because SOPs always have exactly one parameter. So a bijection between functions of one variable and SOPs. Variables of one variable are semantically the same as SOPs, but functions can also be of more than one variable. SOPs cannot. That's one of the reasons for the syntactic difference. Okay, another weirdish thing about functions. So there's no recursion in RASP, which means that RASP is not Turing complete. The fact that there's no recursion means that there will be things in RASP that you cannot implement. Python having recursion means that anything that is computable can be computed in Python. RASP does not have recursion, so there will be things that you cannot compute in RASP. Again, it's an open problem exactly what the boundary is of what things can be computed in RASP and what things cannot. But no recursion, and that's somehow fundamentally why not everything can be implemented in RASP. Okay, so now the actual like fun, interesting part about like what's the cool thing that RASP adds. Everything that we've seen so far has been somehow like just RASP is limited from Python, different than Python in weird ways, has weird error messages, and there are things that you cannot do. But now what are the things that you can do in RASP that you cannot do in Python? That's what this complex control flow section is about. And there are 2 functions, and these are not SOPs, they are functions that are built into RASP. And from these 2 functions, we can implement all of the different types of control flow that we might want to do. And these turn out to be correspond to certain parts of the transformer architecture. Again, right now we're just going to talk about what these 2 functions, select and aggregate, what they do, what are the mechanics of them, how do you use them, and later on we will talk about how do these actually map onto the transformer architecture. So these 2 functions, there is no analog for these functions in other programming languages like Python or C or Java or any other programming language. They exist only in RASP. Not all programs can be written using these functions. And again, if you understand exactly the limits of these functions, then you understand the limits of what a transformer can do. And the whole purpose of why Gale Weiss implemented this language was to really explore these two functions and what it means to program with these two functions. So first, the select function. Select constructs a Boolean matrix from two input SOPs and a comparison operation. So let's take a look at this example right here. Maybe first, let's make sure my set example is just something small like hello right there. And select tokens, comma equals like this. Run that. And let me adjust the screen width just a little bit. There we go. Now it all fits. So, and let's add a bunch of blank lines here, rerun this. So I have two SOPs here, tokens and tokens. Again, the tokens is just a sequence of letters, HELLO. And the select operator takes the leftmost of these sequence, arranges them as the rows of the matrix, and the rightmost of the input here, and arranges them as the columns of the matrix. And then element-wise, between the two sequences, it compares them using this comparison operator right here. In this case, it's the equals, so we get a 1 here representing true if these two entries are equal. In this case, h is equal to h, so we get a 1. Internally, this is actually a true value. So I don't know, writing this out as like a t might have been a better thing to do. But 1 here means true. Anything where you have a blank, that means that we get a false. So e here, not equal to h, so that is blank. E is equal to e, so we get a 1 here. In this case with the equals, since these two things are the exact same input, the diagonal here will always be all 1s, no matter what the input tokens are. But in this case, we do have some duplicates. The L is in here twice, and so we get this little block right here of true values from L is equal to this L, giving this one right here, and this L is equal to this L, giving the other one right here. Maybe a sneak peek about how this is related to the transformer architecture is that the select over here, these are the keys. The K matrix corresponds to this, and the values will correspond to this. But that's not something that's going to be important for now. The important thing is just the mechanics of how do we construct this. So there's an example with the equals. We can use the less than or equals as well. Before I go on to indices, I'll just show that you can do that with string types as well. You can do less than or equals on strings like tokens like this. If we do that, we get something that looks like this. The less than or equal to is happening on an ASCII level. So here the E is before H ASCII-betically. And so we get the 1 right here. H is after E ASCII-betically, so we get the blank right here. This actual example right here on indices like this gives us this triangular matrix with all the 1s down here, because again, indices doesn't care about what the input tokens actually are. It's always going to be 0, 1, 2, 3, 4. So the output of this select statement being this doesn't depend at all on the contents of tokens. It only depends on the length of our example. The length of the example determines how big the matrix down here will be. Again, all of our SOPs have to be sequences of length n, and so the output of select, which is called a selector, will be a matrix of size n by n. Any questions so far? Again, the why do we care about this is probably very hard to grasp at this point, but focus on understanding the mechanics of the what is going on. And once we see a bunch of what's, then we can start talking about putting it together and doing interesting things and explain the why at that point. But if you don't understand the what, if the mechanics of what this is doing don't make sense, you definitely won't be able to understand the why. That a hand? Oh.
Yeah. So if you had, if it was, what was the end event length?
So all SOPs are always of the same length, which is going to be what the length of whatever your set example keyword is. So if I do set example here of ABC, something length 3 like that, and I rerun this command up here, that changed the length of my indices SOPs. They were previously length 5. They are now length 3. And so when I hit enter right here, my matrix over here is 3 by 3.
Is it possible to have like two different, I guess, the thinking of so that the different variable inputs for the parameters versus 1, 2?
So it is not possible to have something over here be of different sizes, but it is possible to have things over here not be exactly the same. So I could have, for example, indices and tokens. In this case, the indices and the tokens are never equal to each other because the tokens are strings and the indices are numbers. And so we get all false everywhere. We could do something like indices and indices plus 1. And that gives me this sort of like off diagonalish diagonal thing. And in general, like all the interesting stuff with this select operator will happen when like there's sort of complicated functions inside of here. So these will always be SOPs of some length, but they can be different. The contents can be different, but their size is always guaranteed to be the same. Yeah, good question. Other questions so far? Okay, let's see. One of the things that turns out to be useful syntactic sugar, we've sort of seen this syntactic sugar so far, but if you have just an individual value, so here is an L in double quotes, that gets what we call broadcast into being a full SOP. So this is a, when you have one value, it gets expanded into a sequence of length n where the entire thing is that value inside of this select operator. So if I do select tokens L like this equals, and reduce set example hello, then that this L right here is L everywhere, and so all of these are equal to L.
So the row thing that was, or I guess the columns, is this supposed to be all L's?
Yeah, so here the columns, this is the thing that's actually being interpreted over here is all L's. But yeah, it's just showing the actual value of tokens. I believe it always puts the actual value of tokens over here, no matter what, even if we...
The L's.
Yeah, no matter what it's computed with, it just puts the actual, like whatever the tokens primitive is right there, whatever your example is. Yeah, so that's something that could be made more ergonomic, but is not ergonomic. Yeah. Good question. Yes, Avizer.
For this example, it would be one only if there's L on both sides, right? Then, why doesn't it do a one for the L row?
Let's see. So the way I think about what's displayed here is that this is just a like a helpful thing so that we can see what the original like tokens value was, but this is not the actual input to the selector. Like really what's the input to the selector here is an L in every one of these positions. Every one of these columns is an L. And so the L for the first row matches the L right here. And yeah, it's so even though it displays hello right here, it's not actually doing comparisons with hello. It's just put the word hello here because that's what the example tokens value is.
Why is that helpful? Like for to say hello to the L?
Oh, it would probably be more helpful to say L right here. It's just the authors were busy doing other stuff and not making things ergonomic.
Like this is an example, it is just like.
Yeah, here the actual computation here, this L is L's everywhere. This sequence over here is L's everywhere. Each one of these rows that it's doing a comparison with is L's. If we do, let's see, like L compared to L, then everything, all the columns are L's, all the rows are L's, and so we get this ones everywhere thing, even though it says hello up here. I did check this morning, actually, the repository, even though it's an old one. There's some recent pull requests that have been accepted as of like just 2 weeks ago. And so your final project, instead of just like actual writing RASP code, you could try to modify their code, for example, to make it more ergonomic in different ways. One of those being like actually put the sequence over here that's been used instead of just the tokens. That's probably on the harder end of projects though, because there's something like 10,000 lines of code in the RASP interpreter, and figuring out what exactly, it'll be like a 1 or 2 line change, but figuring out what exactly the right line to change is to do that would be hard. Okay, we got about 5-ish minutes left. We'll get through the mechanics of the this control flow stuff, and then we'll talk about more of the why stuff, why we care on Wednesday. This gotcha right here. So again, all of the code that you write needs to be perfectly generic in terms of how big the input sequence is. So what that means is that you can never provide an explicit sequence to the select operator. There will be situations where this is a very useful thing to do, but it is something that we can't do. If we do this, you'll get a weird error message about can't create a sequence, blah, blah, blah. Everything that you pass into a select has to be an SOP that is somehow derived from indices or tokens. And you cannot like manually enter a sequence like this. The reason you can't do this is because we need to be generic on the size of the input. Sequences can only have exactly length n and no other size. And here indices has length 5 because our input is hello. Here we're trying to create a sequence of length 3, but that's not well defined in RASP, and so it doesn't make sense. So the arguments to select, you can never like manually create a sequence. You always have to somehow build things up out of indices and tokens. Let's see, we'll skip down a little bit to talk about this aggregate function a little bit. So the aggregate function converts a selector back into an SOP. So the general control flow always looks like starting with your SOP, tokens or indices, doing a bunch of stuff, creating a selector, then creating an aggregator, then back to SOP. So SOP selector aggregate, SOP selector aggregate, and repeating those over and over again. Yeah, we'll just mechanically real quick see what this aggregate does and then talk about the why. So here, see this example selector right here. So we're doing select indices and indices less than or equal to. That'll give me this triangular sort of shape. Again, it's displaying the tokens rather than the indices in these columns and rows right here. We get this sort of triangular shape about when this indices is less than or equal to this indices. And what the aggregate does is it takes a selector like this and it squishes all the rows together, averaging these the values of these rows together. And when it does that, whatever we pass as the rightmost, let's see, so the aggregate function takes 2 arguments, the selector here, which is the matrix, and then the rightmost argument here, indices, is the things that will get squished together. So indices right here for, let's remind ourselves, what does indices look like? It goes 0, 1, 2, 3, 4. We'll have 0, 1, 2, 3, 4 right here. Because all of these values are equal to true, we're going to keep every value in the indices when we squish them together, and then we will average these results. So this will be 0, 1, 2, 3, 4, all averaged together is what we'll get as our last element down here after the aggregate. The first element up here, we have a 1 only in the first position, a 1 only in this position. So only this position is true, only this position will be kept. So we will average the 0 with itself and nothing else. The E position right here, the second position, will average the first 2 positions together. The 0 and the 1 will average those together and get 0.5. We'll run that here, aggregate selector indices. So again, this 0 comes from the fact that the very first position, this position corresponds to the first row up here. And the indices right here, 0 in the indices, keep the 0, average it with itself, which is just 0. Then this has 2 positions right here, 1 and 1. Average these first 2 positions together, a 0 and 1, and we get 0.5 right here. The last one down here, 5 trues. Every position down here has a true associated with it. So every one of these positions will be averaged together. And that gives us a value of 2 if you average all of these things together. Yeah, I'll say that it took me a long time, like probably 20 minutes of playing around with this to feel like I was moderately comfortable with what this aggregate function actually did. So the way for you all to get comfortable with it is just to play around with it. Try to create your own set of selectors that does something simple, like a triangle like this, or full ones everywhere, or some of the selectors that we've just seen up above in these examples, and try to understand what this aggregate would look like on that selector. And you're not going to understand the aggregate function by listening to somebody explain it to you. You're going to understand it from like playing around with it yourself and just seeing what the weird edge case stuff that can happen is. We're pretty much out of time today, so I'll ask that you all do that for class on Wednesday. Try to get to the point where you have some comfort with the select and the aggregator and just the mechanics of what they do. Wednesday, we'll talk more about examples of why we care about that. We'll see a bunch of examples of interesting functions that you can actually implement with all this, but you're not going to be able to follow along with that if you're not comfortable with what the mechanics of these functions are doing. If anybody has questions about other things, stick around and get those answered. But we're pretty much out of time, so I guess we'll end 2 minutes early. And if you do have questions about this or anything else, happy to stick around and get those answered.